Yeah, so I'm Rex Klentzman. I'm a professional engineer licensed in Texas, and I work out of the corporate office for URETEK ICR. We are the chemical grouting company that Corey was talking about earlier in the last portion of his discussion. Um, and I'm the engineering support manager, so I get to come in and assist on projects across the country, and try and head up some testing that we're working on. And just basically, I get to be the guy for URETEK when it comes to engineering issues across the country. So it's really exciting, and man, we got some great stuff to show you guys about what we've been doing and different applications. So I'm glad to be here, and here we go. Today we're going to give you a brief background on URETEK and kind of where it came from, where it's been, where we're going, both kind of new applications and also just a history, show you how long we've been around. And then I'm going to look at an overview of some of our different types of applications. Basically, I think that the best way to look at this stuff is to see it. So I'm going to show you a bunch of pictures, talk specifically about the images that we're seeing, show exactly what we've done, to give you a good idea and a good feel, kind of a good hands-on over this webinar of what URETEK can do, and kind of get your creative juices going about how can we use this on some of our projects that we've got going on. Then I'm going to go in depth, so I'm going to do an overview on all the applications, well, on some of the applications. We haven't, seems like I'm getting calls about can we do this all the time, so I'm not going to say it's all the applications, but it is some of the more major applications of the URETEK structural chemical grout. We're going to do an in-depth look at URETEK Deep Injection, which is where we inject our chemical grout, high structural resin, deep into the soil in order to compact and infiltrate and fill voids and stabilize soils. And we have some really good projects on that. And I'm going to talk about how the different soil conditions really play a huge role in the way that the process will improve the weak soils. Then I'm going to give a little overview on what bearing capacity means, and then I'm going to give an overview on what URETEK soil modulus testing we have done. Soil modulus is an interesting animal, so we're going to look at that and try and get our heads around what a modulus is. So we're gonna look at the Schmertman method calculations. I think I misspelled it there, but I'm sure it will autocorrect if you try and Google it. This is a guy who really pioneered the grouting industry, kind of research on grouting industry in the 70s, and he came up with also some calculations for settlement, and his calculations are very accepted in the industry. We'll look at some textbooks about how much kind of a history he has, and we'll also look at his actual how he puts those calculations together, and then conclusion. So here we go. URETEK, 1979. URETEK, which is basically the injection of polyurethane or rigid structural polymer into the ground beneath the slab. That came in 1979 was whenever it was patented in the U.S. first time. 1988, URETEK USA was granted the exclusive license rights in U.S. and Mexico. So we hold in 1988, we had the exclusive rights to inject polyurethane into the soil. What's known as polyjacking now was just the URETEK method back then. So we've been doing it for, coming up on 30 years. So we've got, in the year 2000, we noticed that, the powers that be noticed that there was an industry that we weren't really going after, which is buildings and residential, industrial, commercial projects because there was a plethora of Department of Transportation projects that were a lot larger and there was more money to be made. We weren't able to take advantage of the opportunities out there in the residential, commercial, and industrial, and so we started to go after that, which with URETEK ICR, a new company that was established in 2000. 2003, the URETEK Deep Injection was invented and patented, came over from Europe, and it's patented, and that patent's held, is used by us by URETEK exclusively in the U.S. 2006, the ICRs, the industrial, commercial, residential, covered all 50 states. 2009, we did a lot of projects, been around for a long time. 2010, we got ANSI certified, and now here we are exploring exciting new projects and exciting new methods in order to keep this stuff moving forward and trying to educate our partners and potential clients and just kind of the public about what we can do. So let's move on. So applications overview. We're really good at restoring and increasing soil bearing capacity for existing structures. That could be structural footings, it can be slabs, and including, as Corey pointed out in the case study back then, at the end of his presentation, bridge footings is something that we're very good at restoring, as well as URETEK USA, who still does a lot of the bridge approaches, but we can come in and we can fix those bridge footings. We can halt settlement caused by weak load-bearing soils, and we're real good at, like Corey was talking about, infrastructure stabilization, soil erosion remediation, stormwater infrastructure restoration, and emergency infrastructure restoration, as you'll see in a couple of these case studies we're going to talk through. Manhole and joint and lateral sealing. Corey kind of touched on that, but we can do it. Here's an example of a manhole that was experiencing pretty significant I&I. It was an older brick manhole. It was just leaking water through the mortar joints. We came in the outside, injected around, and you can see that we filled the voids. Stop that I&I in its tracks, and the stuff lasts really long. Lateral sealing as well. You can see this. You can see this pipe up on the right that was TV'd, and you can see that on the top left you can see some of the water coming in. On the bottom right, on the top right, you can see we injected, and there's some polymer coming in and filling the path of the water flows. And we come in from the outside, from the top of ground, no excavation, inject above the pipe, and because the polymer is a liquid whenever it's injected, it will follow wherever the water is going. It really seeks out those voids. So it does a great job of following where the water is and sealing up. It's hardening within 30 seconds, less than that. So we have very, very strong control over where the polymer goes, and also we can shut it off right whenever we want to, because it's such a quick reacting material. Quick note on I&I. Corey said we saved them $100,000 on a particular project by treating, I think, 7 manholes. That was $100,000 a month, but what you also have to take into account there is that you expand the capacity of your wastewater treatment plant, and you don't have to go and upgrade and build a new wastewater treatment plant as soon. So you can postpone, you can push that back, by years if you can cut down the I&I in your system, and we can really help cut down the I&I in the system. So it's not just the $100,000 a month in treatment that you had to pay. It's also you're able to put off having to build a new $30 million wastewater treatment plant facility for 5 more years. So that's another advantage to getting your I&I taken care of, and URETEK is really good at taking care of I&I with no disruption of service. Kind of another one that you guys have seen a couple before. Here's another one that Corey showed a case study of. We have some water coming in the joints. We're able to fill it up Emergency infrastructure is a project in Houston that was in dire shape because it had a lot of I&I coming in through it was penetrating and erosion coming in through the joints around the storm sewer, around the large box culverts. You can see kind of in that top right image, it's it's a computer animation of the voids that were around the pipe, and then the bottom right is a post, voids filled by the rigid chemical grout structural polymer that URETEK uses, that's just aggressively seeking out those voids because it's going to follow the path of least resistance. It's going to try and find that lower pressure. You put it down in the ground, it starts expanding. It's still in a liquid to kind of like a milk-shaky consistency, and as it expands, it exerts pressure on the surrounding soils, and it will seek out those voids as it expands, finding the larger voids first, which we'll look at a little bit more. This is a really interesting one. It's another box culvert, and you can see in the left picture, it's a stream that is flowing, but it flows under the culvert. It's flowing through your backfill, eroding and taking out all your structural stability because the flow is going under the culvert. It's really just taking out everything that your culvert is sitting on, and that's not going to be healthy for the lifespan of your culvert or any structure that's on top of it if it's a roadway. So we came in and injected the URETEK polymer structural grout basically directly into that soil, and filled the voids while the water was flowing through it. So we're hydro insensitive, so we will react in the water, which is not a problem for us. And we sealed that up, and if you look on the image on the right, the water is no longer flowing under the pipe, under the culvert, but it's flowing through the culvert where it's supposed to, protecting and stabilizing the life of that structure. So that's a significant project where we're able to come in and basically rescue this box culvert from needing to be replaced. So we're talking about filling voids, seeking out voids, and stabilizing. So this is another thing that happens where we stabilize this spillway. They were seeing the same type of thing, water coming through around the pipe instead of through the pipe, and that is taking out your structural fill in there and giving you some serious problems with your dam stability. And if we have any infrastructure engineers here, you know how big a deal dam stability is. It's public safety. It's a health safety issue, and those are things that cannot be left alone. They have to be taken care of, health safety issues. You've got to drop everything and take care of your health safety issues. So dam spillway stabilizations, I mean, that's why this previous project right here I was talking about, the Army Corps of Engineers called us in. They noticed the problem on Thursday. They called us in. We were there on Friday working on it because it was a health safety issue, and you cannot let those things sit. You cannot let a health safety issue sit. Another example, sealing behind voids, basically using the polymer to seek out voids and solidify and stabilize. Okay. Now we're going to talk about URETEK Deep Injection. Those are some pretty cool infrastructure applications. I kind of skipped over our bread and butter because I'm directing this more to the engineers, more to the what do we do deep into the soil is kind of what this webinar is about. But I'm kind of skipping over the URETEK method, where we're able to really lift sunken concrete. It's the basic, it's kind of the bread and butter of the polyjacking industry, and URETEK is as we said before, is the pioneer of that industry. So we're really good at picking things up. Like Corey showed you that box culvert that they picked up 24 inches using URETEK method and deep injection in combination to both compact that subgrade and also apply a bulb pressure onto the bottom of the culvert and lift it. So it's very powerful, very powerful. So URETEK Deep Injection, increasing bearing capacity and halting settlement. Let's look at this little. This is kind of an animation that I'll queue up, and I'll talk over it while it does something. This is looking at a house. Now we've got our nice little cross section there through our graphic department. So what we do is, obviously it's not just one person. We have somebody on a drill. They'll drill a hole through the footing, through the slab if it's necessary, and then we'll install the probe, which is a half-inch steel rod, to the injection depth, and inject and get our polymer down to depth so that it can fill the voids and find out the best. It'll really seek out those voids and compact the surrounding soils and give you some great stability. Now we're going to talk about these bulbs that we're showing down there in the soil. That's kind of laboratory setting type things. That's not what happens in real life. In real life, what happens whenever you inject this polymer into the soil, as you can imagine, because soil conditions are so variable, so is the way that an injected grout will behave. It's very variable depending upon the void space available within the soil, the moisture content, the strength of the soil. Just imagine, trying to blow up, dropping that polymer down in there and it expanding and being able to go just seek out the low pressure. So it goes in a bunch of different locations. And this is a video that it might be a little choppy on your screen, but it's kind of slow, so I think you'll be able to see it. This is an illustration. It's a test that was run in our Tomball office a couple months ago. There is an injection rig, injection gun at the top of this soil box. The half-inch steel tube is driven halfway down that box to the intersection of that brownish to the dark brown and the light brown sand. So kind of the pea gravel, which you'll see, and the sand down in there. That's where the injection is occurring. And so I'm going to hit play on this thing, and you're not going to hear any noise. I'm just going to keep talking over it. So we're injecting, and you can see how the polymer is seeking out the largest voids first. It's going to the lowest pressure, so the polymer is down there. It's expanding. And the first thing it wants to do is find the largest voids because, and it's displacing the air. If there was water in there, it would be displacing the water. It's just pushing everything out of the way, and it's trying to find that largest void. And you can kind of see on the left, mid-left, it's getting down into the pea gravel. It's filled the largest voids, and now it's going into the mid-sized voids, kind of the space between the pea gravel, gravel aggregates. If you can imagine the deep injection in this kind of granular soil, it's a lot like cementitious concrete, in that the strength from the concrete comes whenever, like if you just apply a load to cement with no aggregate in it, then now we're still injecting, we're still filling those large voids. In just a second, you're going to see that it hits to those smaller voids. If you apply pressure just to the cement, then it's not very strong. Like, it won't hold a load. But if you throw that aggregate in it and make it concrete, then the cement is the binder. There it is. So it's finding those smaller voids. The cement is the binder that holds those aggregates together, which allows the aggregates, which are very strong rock, to stick together and form a very strong matrix of cement and aggregate. We can do the same type of thing where we can capitalize on the strength of the existing soil or the existing sand, the existing gravel, to hold it together and really apply, set it up so that it can hold that load. Now you can see it's starting to get into the sand. It's going after the smaller voids. So I think that's a good illustration of showing how the polymer is going to work. It's going to go to the follow the path of least resistance. It's going to go after the larger voids first, and then it's going to go after the smaller voids because those are higher pressure systems. Smaller void is the higher pressure to get down in there. So it's going to fill the larger voids first, and then go to the smaller voids. So let's look at a couple applications. We have this application here where there's another test box showing URETEK injected into a layer of aggregate, and this is injected directly into sand. You can see how it's formed. It's really bound that sand together, and it's given us a really great, very strong load-bearing system in there. This is an example of injecting into very weak soils, like no friction angle. This is peat. And the idea here is to inject between the stronger sand layers. It's about 2 feet of peat, and there's a strong sand layer above and a strong sand layer below. So we're injecting directly into that peat, and the polymer is going the path of least resistance, which is usually up, where there's less hydrostatic pressure. So it forms these fins, and our concept here is to create a honeycomb where we will transition the load from the higher bearing soil strata above to the higher bearing soil strata below, and basically take the low bearing, the very weak peat layer out of play, because that load is now on our soil, on our polymer fins. Here's another test box, polymer fins and peat. I'm trying to get through this because I don't want to miss. This is pretty cool. Stabilized crater repair. Basically, the military had an issue with IEDs on roadways, and they wanted to an IED explodes, creates a crater in the roadway. They want to be able to get a dozer, push all that junk back in there, and then build a road on top of it and move on. But because it's not compacted in 6-inch lifts, obviously it's not structural fill. It's just whatever's around. They dump it down in there. They want to be able to mobilize quickly. So they brought us in. They had this idea that they would create a simulated crater, just push all the gunk back into it, and URETEK would come in and inject it. So they did that, pushed all the junk back into it. URETEK came in, injected. We removed it. This is what it looked like. This is just debris. This is weak soils, not compacted. This is boulders. This is old concrete that was destroyed in the explosion. We injected it and removed the crater whole. So that's a significant bearing capacity increase. Significant, kind of illustrated there. This is the edge of that polymer, the edge of that crater repair. Basically, the polymer infiltrated into the native soil, the higher compacted native soil, and you can see the polymer veins that were tying that all together. And this is kind of how it behaves in areas where there's not that void space like there is in granular soils, like in silt and sandy clays or silty clays. It will create stringers and move out there. Here's another example. So it's a complex issue. Depending on your soil type, depending on what's going down there, the polymer is going to behave differently. All right, now to the meat in the last 10 minutes. Allowable bearing capacity is what I want to talk about. What is it? What does it mean? Whenever somebody says, I got 2 tons soil here, or I have, 1 ton soil and I need 5 tons soil in order to build, what does that mean? Allowable bearing capacity. So It's the load a soil is capable of carrying without a shear failure and without resulting settlements being tolerant for the built structure. So in order to understand what that means, you got to check two things. You got to check that it's not going to fail under shear, which means it's not going to collapse. And you also got to check and note that the settlement, that primarily the intolerable settlements, is going to be differential settlement throughout your building. But also, depending on the structure, you don't want your overall settlement to be too much either. So we're going to look a little bit about what is a shear failure and what is intolerable settlement. Here's allowable bearing capacity shear failure. This is kind of a famous one as far as civil engineering goes. It's the Toscana grain elevator. The load was excessive, that the foundation punched directly into the ground and caused the structure to rotate. I think this particular case had differential settlement first, and then it collapsed within, this happened in like 2 days. It happened very quickly. Shear failure is very quick. It's whenever the soil is massively overloaded. The soil was massively overloaded. It was built on an old riverbed, basically. And this is intolerable settlement. We all know about the Leaning Tower of Pisa, and it's been settling for 300 years. No, longer than that, 500 years. No, construction started in like the 1100 or 1300s, I think. So it's a very old structure. It's been settling for a very long time, and it continues to settle, and there's a lot going on here. So it occurs when the foundation increases, the load on the foundation increases the stress in the soil mass and causes soil particle rolling, sliding, crushing, and elastic distortions. So over time, when you apply a load, the soil particles move around and settle into place, and there's these elastic distortions, and it's compacted and goes down in there. So it's kind of it's a slower failure than shear failure, and it's one that can be caught and treated. So it's a very different animal, and if you can picture it in your mind, the amount of load that's going to require, the amount of load that would be required to get on the the amount of load that would be required to cause settlement is significantly less than to cause bearing capacity failure. Okay. Interesting note: Mussolini, Leaning Tower of Pisa, in 1930s, he didn't like that the tower leaned. He wanted to fix it, so he came in and drilled holes in the foundation and dumped hundreds of thousands of pounds of concrete down into the foundation, pumped it down in there, and it actually made the problem worse. So Mussolini tried to mudjack the Leaning Tower of Pisa and made it worse. So lots of ways to calculate bearing capacity is what I want to get to here. Lots of different formulas that can be used, and there's not one set formula that's used to compute allowable bearing capacity. So that depends on the experience of the engineer and who they're going to select. There was a thing at Texas A&M where they invited a bunch of geotechs in and looked at a foundation and said, "We're going to load this up. Tell us how much load this can take before it settles a quarter of an inch." And so they did that. Everybody ran their calculations. They had 40 different ways to calculate it, and they were all different. And they measured it, and the most effective one for calculating settlement was the Klentzman method, which is the one that we're going to look at. This is a quick example. We prepared another injection box, took the sides off. It's strong. Loaded it up with an excavator, and it didn't crush. Loaded it up with an excavator. I mean, if that was just soil, you don't even need to load it up with an excavator to crush it. That's an illustration, anecdotal evidence of how strong it is. Okay, so we've done testing. Klentzman method, one of the biggest things that it uses is the soil modulus, which is how squishy the soil is. The soil modulus is how squishy the soil is. better known as in engineering circles as the slope of the stress-strain curve, how quickly it strains when you apply a stress, okay? So that's what the soil modulus is. We've done testing on sand, on granular soils, to show that post-injection, URETEK soil modulus will increase by 700% at a minimum, depending on the existing soil conditions. So we can get that soil modulus from 2,900 psi to 62,000 psi, and that is the primary primary soil property that's used to calculate settlement in the Klentzman method. And if you can see here that E sub S in that calculation, that is going to be your modulus. So we can increase that modulus in order to decrease your delta H is settlement for a given load. Increase that modulus, decrease the settlement for a given load, which means if you decrease the settlement for a given load, if you have an allowable settlement already, you can increase the load that you can place on that for that allowable settlement. Okay, so here is a quick example of the Klentzman method being done on a typical 2 foot by 2 foot square footing. Okay, 2 foot by 2 foot square footing, and for this example we said normally consolidated sand, just picked an N equals 6, which correlates to an E of 36 tons per square foot, which that E comes from tables that have been used for ages. That is, I got mine out of Foundation Analysis and Design by Joseph E. Bowles, one of my geotechnical textbooks from school. So you can see we're applying 5.5 kips per square foot to this footing, and we get 1 inch of settlement with sand, no polymer. 5.5 kips to 1 inch of settlement, okay, with only sand, no polymer. We're going to do 1 injection depth, okay? We do 1 injection depth. We're going to treat the top 4 feet. So at the top 4 feet of this project, we're going to keep the bottom 4 feet the same. The Klentzman method uses what they call a strain influence diagram, so they only look at the area where the strain is being affected in the soil. You don't look down to infinity. There's a calculation that comes up, and in this Klentzman method, in this project, we go down to 8 feet is where the strain influence is nearly nothing, so we're only looking at the top 8 feet for a 2 by 2 footing. So here we go. We've increased you see this E, the E has gone from 105 to 4,464 in the top 4 feet because we've applied the URETEK polymer. So that means that we can get 13 kips per square foot, which is 6.5 tons per square foot for that same 1 inch of settlement. So you were at 2.2, now we're at 6.5 by treating just the top level 1 injection depth by increasing that 1 layer. And then we go here and we're like, okay, well we went from 13 kips, 6.5 tons with 1 injection. We still have a squishy layer of sand, of weak sand in that strain influence area. Let's go and let's treat the entire strain influence area, the entire area that empirical data says is affected by a 2 by 2 square footing. So we're going to put URETEK 2 different injection depths, and it locks that whole place up, locks it all up. 30 kips per square foot or 15 tons, you only get 0.2 inches of total settlement based on the Klentzman method. I didn't go down to 1 inch of total to see how much it takes to get 1 inch of total settlement, because it's like 100 kips or 50 tons, and that's just not something that you're ever going to come into contact with. You don't ever want to put that much load on the soil. But in order to get 15 tons, according to this, of bearing capacity, you only get 0.2 inches of total settlement. This is Klentzman method. Look it up. I didn't go into all detail on the calculations because it's really boring and you guys would have glazed off more than you already have. But that's my presentation. I know that I'm coming up on my time here. I just wanted you guys to see, based on the Klentzman method, which is a very acceptable method for calculating settlement in geotechnical soils, we can go from an inch of settlement with 5.5 kips per square foot to 0.2 inches of settlement with 30 kips per square foot. So that's what I wanted to share with you guys. And that's the takeaway, man. That's why I left it to the end is, there you go, 5.5 for an inch, 0.2 for 30. Okay. I'm done. Thank you very much. Questions?
Yeah, I think Corey's going to change over the screen.
You gonna take it away, man?
Yes. Corey, did you want to make a comment? You're on mute at the moment if you're trying to speak.
Yeah, thank you very much, Rex, for going over really those calculations and just showing some of the data behind it all. A couple project profiles I just want to show before we go into questions is we did this particular project 15 years ago in Kentucky, where that milk silo needed to increase the bearing capacity of the soil stabilized because it's starting to settle. And the neat part is HDR, a very reputable third-party engineering company that's national that many of us know, did a survey in December 2015 where, as you can see by the highlighted text in red, that it appears from their survey elevation that there's been minimal settlement since March 2001. So we were in fact able to be successful in that particular project. Another project that's neat where buildings are changing. The use of them are changing. Additional loads are being put on them. Maybe they're adding another floor or a mezzanine. Whatever the case may be, the buildings are changing. This particular case for University of Tennessee, it was an abandoned building for many years, so the roof had openings, rainwater would come in, it would begin to get underneath the slabs, cause erosion underneath the footings. So not only did you have the combination of deteriorated soil site conditions, you also had the change of a building. And so University of Tennessee bought this land or this building and wanted to change it. So we came in, increased the bearing capacity using chemical grout underneath 140 columns, and we're able to satisfy the customer, and they since have completed the building. And here's a recent project, or not a recent project, a project was done a couple years ago, but the building was constructed in the late 1800s, and wood timbers were part of the footings. The building still functions, but they had to be due to additional loads they're putting on the floors. They needed to increase the bearing capacity, so we were able to come with chemical grout, which is much less invasive than some of the other solutions that they're going to have to consider. So we were able to increase that bearing capacity. So let's open up the questions, Robert, before we close out.
Okay, great. I first want to answer just a quick logistical question that's asked here is, will the presentation be taped or available afterwards? We will be sending out a email that has a link to a feedback form on our website, especially for those who are seeking PDH certificates for this presentation. And then once you filled out that form, it'll give you access to a video of recording of this webinar, as well as all the materials that were presented as well. So I'll go ahead and go into it. So there's a few questions regarding clay soils, and this one pretty well covers it. If you can cover if this injection method is effective in clay soils or just granular, that would be appreciated.
Yeah, sure. That's a great question. We are effective in clay soils. The issue with testing clay soils is that and that's something that I'm very much on the taking the initiative in order to get into. The issue with testing clay soils is that because those fines are there and there's no voids for us to create that cementitious kind of that concrete matrix, it behaves significantly differently. It seeks out voids by compressing the surrounding soils and creates its own voids, and so it does this lensing and it strings out, and it increases the capacity of the soil mass as a whole as opposed to one point location. And at this point, pretty much the majority of geotechnical testing tools test at a point, and then extrapolate that across the entire soil mass. So it's more difficult to quantify injections in clay soils. However, I mean, like you can look at our past history, injections in clay soils very much do work, and do increase bearing capacity. We have seen some very, very promising results of it from injecting in clay soils under roadways, by testing pre and post testing with the falling weight deflectometer. It's a trailer pull device that drops a weight on the pavement and measures the deflection, and from that will derive a composite soil / pavement modulus, and before and after injection testing with the falling weight deflectometer has been very successful. So it does work. It's harder to quantify the increase in the modulus in order to use the Schmertzman method like we do with granular soils, because you can't just pull up a one little, what would you call it? You can't just pull up a specimen and take it to a lab and test it, because it hits the soil mass as a whole as opposed to improving it at a point.
Okay, great. Next question, does the industry consider the urethane injection as a type of permanent confinement system, or do additional measures need to be taken regarding the stream under the spillway, for instance?
That was a polyurethane only. It goes in there. Polyurethane is the chemical grout that we use is very permanent. Yeah, and we can contact me directly or contact Corey or your local URETEK representative, and they can get you the studies that we've done on the permanency of this solution. There are some examples where it's best to combine technologies. URETEK is not the solution for every problem, but at the same time, whenever it's applied correctly, then it can be permanent.
Does this material work for dealing with liquefiable soils?
That's something we're looking into. That's something we're looking into right now. And
I'm sorry, I put myself on mute for a second, Rex. What is the % of bearing capacity increase we can get from this polymer?
Well, in the example, it depends significantly on your existing soil conditions. If you've got pretty strong soils to begin with, then you're going to have a smaller percentage increase. If you have weak soils to begin with, we're going to have a strong percentage increase. 800% according to our testing, and according to our past history of like the 15-year-old project that was experiencing excessive settlement that Corey just mentioned, and they came back 15 years and there's been 0 settlement. That's a massive increase in capacity in order to go from excessive settlement to 0 settlement after 15 years. But in the calculation I just showed you guys, we went from 5.5 kips to 30 kips per square foot.
This is Corey. It is noon Eastern, so just to honor all of your time, we said this would be over at noon. If you need to go, please feel free to stop, hang up. And a couple things. We do have a upcoming webinar Friday, August 19th at 11 a.m. We'll talk about our injectable barriers, and where we are using chemical grout, putting them at various elevations and multiple rows to create a basically a vertical barrier from contaminants or water going from an unwanted area to the other. And also on social media, Facebook, LinkedIn, Twitter, obviously all those, please follow us, stay engaged. And all of you, thank you very much. please fill out the survey. We'll give you the PDHs and look forward to seeing you on the next webinar. For those who want to stay on for more questions, please do. But we definitely, if you've got to go, we want to respect your time. So thank you very much. And Robert, any more questions for Rex?
Yes, there certainly are. And I also want to mention real quick that if you do want to submit a question, if you look in the toolbar of the webinar, you'll see in there it says questions, and you can submit your question there. So I'm going to continue to the next question. Is there a limiting grain size for this to be effective?
Yeah, that was something that we just talked about on why is this thing? That was something we just talked about on does it work in clay soils? So obviously clay soils have grain sizes significantly smaller, but we're still effective. However, the mode of improvement is different. If that makes sense. So not necessarily. There is once you get down to the passing the 200 sieve, it's going to behave significantly differently.
Great. How deep can the URETEK Deep Injection go into sandy soil?
We've gone as deep as 40 feet, and so that's kind of just limited by not necessarily by the soil type, but it's limited more by just kind of our injection setup. If there's an application where we need to go deeper, then we would need to revise our injection setup and try that in a different manner. Would you agree, Corey?
Yeah, absolutely. There are some times that we haven't been able to go. We have gone deeper, but definitely every site's different. We may have to incorporate drillers. But it's more about getting access down there as opposed to the material. And we will, as I mentioned at the very beginning, we'll adjust the temperatures or maybe the material to help delay the reaction curve from taking place, because that's really a big driver, as well as the drilling component.
Yeah, definitely.
Okay. Do you perform initial subsurface investigation before completing injection process, compare before and after results, and to know exactly where you complete the process?
So we will do an initial subsurface investigation. We'll either use an existing geotechnical report and use those boring logs in order to know where the weak soil strata exist, and those are the areas that need the most treatment. But we also have the ability to do initial dynamic cone penetrometer testing so that we as URETEK can determine the location of the weak strata by counting the blow counts as it goes down, as it continuously goes down. So post-verification, dynamic cone penetrometer is not very good on post-verification because, as we said, you can have an area that is highly improved, and it's underneath a foundation. But then there's another area that is not as highly improved underneath the foundation, but that highly improved area is supporting the foundation significantly stronger. That's not to say that we haven't had good results with pre and post testing. It's just not something that we rely upon as a measure of project success, because there is, except for load testing, we've done load testing on treated piers, and it worked. Very treated footings, and we get some really good results from that.
How much chemical grout volume is required for a given modulus increase?
Yeah, that's a good question. So the concept is that we're going to replace the air voids, the air and water voids in that granular soil with polymer. So we will calculate a volume of soil that's going to be treated, come up with a design for an injection pattern that will treat that soil mass in the manner that we want, and then calculate a volume based on replacing the voids with a polymer. So it definitely varies. There's not one answer. It's a site-specific issue. but it is an answer that on a specific project we find. But we're a solutions company. We're not necessarily concerned with how much polymer we get in the ground. We're concerned with fixing your problem. So that's how we look at it.
Would you use GeoPeer over URETEK?
I mean, there's lots of applications. If I wanted to fill a void, if I wanted to do any of these other applications, URETEK is your solution. But there may be some instances where GeoPeer is a good solution as well. But I work for URETEK, so I do URETEK.
What happens to the existing underground utilities?
Well, the existing underground utilities will fill the voids around them, as we're shown. We definitely want to monitor the underground utilities. If there's some if there are utilities within the work zone, we will want to monitor that and ensure that once voids are filled, and if, like we saw in the pictures, I&I is occurring, and we fill the voids, that we're able to, behave appropriately so that we fill those voids without filling up the pipe with polymer. So we need to monitor them. And because the polymer exerts an equalized pressure, it's not going to push on the pipe too hard. It's going to fill the voids around the soil. It's going to exert in all areas. So collapsing underground utilities is not something we're highly concerned about. We're more concerned about if you have a sewer or wastewater line, that we don't fill it up. So we want to monitor them, and we want to be careful if they're within the area of work.
Is this available for residential foundation settlement jobs, or is it just for municipal and industrial projects?
Definitely available for residential. The ICR stands for URETEK ICR. ICR stands for Industrial, Commercial, Residential. We do a lot of residential jobs, and we're very successful, and we're really able to provide a permanent solution to residential homeowners who may, that might not be available under using other technologies.
Okay, so this is a multiple. What's the application spread rate? How far apart are the injection locations? Is that soil dependent as well? Cost, and then what's the cost per cubic foot?
Yeah, it's project dependent. Definitely site specific issue. It's a site specific issue. So we would want to look at your particular project. If there's one that you have going on, contact us, and we can definitely give you a good price and let you know what it's going to cost in order to fix that problem. But yeah, it's very site specific. I couldn't answer it. I couldn't just throw out a number right now because it very much depends on your soil conditions and the soil loading conditions.
What is the impact on global stability, especially if the adjacent area soil conditions are poor?
We're in situations where the global, where the adjacent soil conditions are poor, I'm trying to think of how to answer that. We would look at treating some of the surrounding soils in certain conditions. If you're talking about doing work in a city like New York where you have shared walls, we need to take that into consideration and be sure that we're treating a good enough spread in order to help the rest of in order to not do any harm to any adjacent buildings by stiffening ours and compressing against. So we're definitely doing continuous monitoring on adjacent structures, and we're doing this again. I keep saying it, but on a site by site basis, and we definitely want to look at your project if you got one in mind.
Robert, are we done with questions?
Thanks for that. Can you repair sinkholes in asphalt city streets with injection or URETEK due to clay sewer pipe that may have a cracked bell without damaging the pipe?
So, so that's a two-part repair. You will definitely want to monitor it. You want to use a material, a polymer selection that does less expanding and more void filling, so that it doesn't exert with too much power against the clay pipe. Yeah, that's a solution that we can work on. It may be a combination of technologies, but yeah. As you saw, we repaired a brick manhole, which is kind of similar structural capacity to some of that clay pipe. So it's something we can look at. We want to continuously monitor it during the process and go after it. Anything else?
So there was a slight correction on the leaning tower, or stated anyway. Leaning tower was due to consolidation of clay. Can your product spread out enough in a clay soil to prevent consolidation?
Yeah, definitely. That's I understand that the leaning tower piece of wood is not on granular soils, but consolidation is a key to settlement. Yeah, we can, and it is. But our proof for that is more anecdotal. It's more project history, and it's something that we're looking at as far as how to move forward. And yeah, consolidation. That's one of the reasons why it's been happening over the past years. And also why applying more weight to that clay by putting concrete under the foundation was not helpful. So thanks for the input.
A couple of comments real quick. There's a question saying if the webinar will be available for download. Yes, the webinar will be available for download. Well, the webinar materials will be available for download. You will be able to view the materials as well. Just make sure that when we send the feedback form to you, go into the website, submit to the feedback form, and then you can get access to those materials. Could this create differential settlement at the edge of the improved and unimproved area?
Yeah. If you don't treat all the weak areas, then you will have the URETEK treated. You'll have the URETEK treated areas that's very strong, and then you'll have your existing soil conditions that were weak and had us come in the first place. So it's important to look at the project as a whole, and not look at, hey, I've got this one little problem area. Can you fix just this one little problem area? You got to look at the problem as a whole and know how repairing the big problem is going to impact kind of some smaller, less evident issues surrounding it. So, it could create an instance where you have the strong material in one location and, weaker native soils in another location.
Okay, this is a centripipe question. How thick of a layer can you spin cast with centripipe, and any structural gain, strength gain with centripipe?
Yeah, for centripipe, we will apply the material in 1/2-inch lifts, and as far as the structural gain, yes, there is, and that's the whole idea of centripipe, is to not only give it an aesthetic, renew, but also a structural renew. And so depending on what that soil envelope looks like and the condition of the pipe itself, but more about the soil envelope and the loads that pipe will see, we will work with our engineer to figure out how thick does it need to be. Does it just need to be a 1/2-inch thick, or do we need to go up to 2.5 inches? So it all depends on that side of what we'll do, and we would provide basically an engineered report and a recommendation of what the thickness is. But even if we do a 2.5-inch thick solution, we will still apply it in 1/2-inch thick passes.
And then an additional question related to that, Corey, what is the thickness of this lining? Can it be used to increase the clear cover for reinforcing bars as a retrofit solution?
Yes, the center pipe is applied in two ways. One is with a spinner, which we saw the pictures of with a spinner. The other will be just a hand spray. So kind of think of it like a fire hose, if you will, just doing the hand spray. It's the same material, and so we'll use the spinner for up to 120-inch diameter pipe. But in the event that it's larger, or maybe it's a box culvert, then you can hand spray the same material. And there's a case study we could share that the individual that asked the question. The project was done with Florida DOT and Stantec Engineering out of Florida, where the reinforced concrete box had deteriorated so much that part of the solution was to actually apply basically a wire mesh up against the existing sides of the box and then hand spray for about a 4-inch thickness. So you're almost kind of rebuilding the structure in that sense, but it like how a shotcrete can be applied, but the shotcrete has a low PSI, where we will be using 8,000 PSI or 10,000 PSI material, depending on what the need is, and then hand spraying it. So a lot of different applications that we can do for you.
Is there a way to control side bearing pressure on a foundation wall when injecting under a building slab?
So what we mostly do is we're going to be monitoring that wall in the area of injection, and if there's any deflection, then we'll hold off and ensure that we don't damage that wall. I mean, the polymer is going to follow the path of least resistance, and it's going to expand there. So it's gonna if there's a void adjacent to a wall in the injection area, then it's going to find that void and get there. But after it fills that void, it'll go after the other voids and compact other areas. So that's why it's important to have the person applying these processes make sure that you're going with somebody that has a lot of experience and knows what to look for, because there is the possibility to screw a project up pretty significantly if you don't know what you're doing and if you're not monitoring it appropriately.
This is perhaps a question that's going to apply differently throughout the country, but is there an approximate minimum cost on smaller residential projects?
Yeah, that's going to depend. That's going to depend very much about where you are across the country. I know in Texas we're in the $800 to $1,200 range, but it's different across the country because of mobilization issues and just because of significantly different economic situations. So.
Okay, and then that's it for the questions. Corey, I'll go on just real quick. There was one more about the PDH certs. Again, I'll just remind, after we've closed the webinar, give it about an hour or so, we'll be sending out a follow-up email that's got a link to our survey form on our website. Just fill out that survey form. It'll have the question of if you require a PDH certificate, and then we'll know you'll need one. And then after that, give us about a week, about 5 business days, and then we'll send your PDH certificates out afterward. We just try and do them all in one run and give everybody a reasonable amount of time to submit their surveys. And that's it from my side on the administration, and that's it for the questions.
Excellent. Well, thank you very much, Rex. Thank you for your preparation as well as just presenting to all of our customers today. Greatly appreciate it. And to all of you who definitely spent your Friday with us, thank you very much. Hopefully it was informative. Please continue to send us questions. Stay connected with us on social media. Let us know how we can help you. And we look forward to seeing you August 19th for our next webinar on the injectable barriers. Thank you very much. Have a great weekend and look forward to talking to you with upcoming projects. Thank you. Bye.
Thank you, Corey.